about 220 years ago, the industrial age essentially accomplished its grand mission, which is augment the human muscle, augment and scale it massively, obviously. And I would say that our industry, after now 77 years of sort of information age, if you take those dates, has also found its mission, which is augment and scale the human brain.
Well, thanks for joining us today. Our guest today is Aart de Geus. He's a co-founder of Synopsys, and he just received the very prestigious SIA's Robert Noyce Award. Last night, there was a dinner last night, correct, in San Jose?
Yes, indeed. Yeah, it was.
Yeah, a lot of people attended, I assume.
Yeah, it was pretty full.
One of the things, actually, I was going through the SIA site and tried to figure out who else received this award in the past. And they actually listed a lot of people, including, I think last year it went to the Micron Sanjay, right? And the year before it was Lip Butan. And of course, the usual suspect, the Jensen 1, 2021, and Lisa Su of AMD 2020. So, this list of people, they're all familiar people. Then that got me thinking, why on earth that somebody like you, really the pioneer of EDA industry, had not received the award yet? In other words, that without your EDA tools, semiconductor industry today does not really exist. Is that too far to say that?
Well, the timing of those things is determined by whatever happens in that organization. You have to realize that for many, many years, semiconductors was very focused on the semiconductor companies and their leaders. And no matter what the timing is, it's always an honor. And I love the fact you called the others the usual suspects because our industry, everybody knows everybody, and yes, they are the usual suspects.
In reality, just following up on what Junko said, you've received quite a lot of awards over time, over your career. And I'm, like Junko, I'm surprised you didn't get this before now, but this is like one of those ones, even after you had left as CEO of Synopsys, it must really be good to have received this award, capping some of the other ones you've got in the past.
Well, you make me blush now. The reality with all of these awards, of course, it's an honor and privilege to receive them. But everything we do in our industry is the result of many people working together. And actually, I've often liked to use the terminology that in English we say, success is the sum of our efforts. It's not. It's the product of our efforts. A single zero, and everybody gets zero. And so the team play is not only within one's own company, it is also between companies within the entire ecosystem. And so, when one of the suspects, so to speak, gets recognized, hopefully the other suspects, raise their glass too, because we all know we're completely interdependent and we've all benefited from essentially having brilliant people around us.
That's a very good point. In other words, that the semiconductor industry itself is kind of expanding in a way that, well, back in the days, I think you started your career at GE, right? In those
Indeed.
days, GE actually developed semiconductors.
Amazing, huh?
Yeah, I know. This is like yeah, so things have changed, but now the pendulum swinging back, companies like Apple is designing their own chips, Tesla designing their own chips. So things have changed. You have seen this pendulum swing one way from the other. So I thought this would be the good opportunity to talk about really the changes you have observed over the last, I don't know how many years, 50 years, 40 years?
let's make it 40. Yeah, with the end of school, it was 50 years.
All right. So what have you seen the most notable? I mean, I'm just surprised when I read that you are with GE and you're already actually working on the design tools then.
Well, it's interesting that you realize that GE was in semiconductors. Most people don't know that. And at that time, GE had this vision of the factory of the future. And the CEO of that time invested in multiple technologies, including semiconductors. And I happened to be a low-level, first-level manager straight out of school with a small R&D group at that time. And the development of synthesis, which turned out to be one of the linchpins for the future, happened there. And then 18 months later, GE decided to get out of semiconductors. And I think what they didn't like about the semiconductor industry was the high degree of economic variability for conglomerates that was, doing dividends for people and was a fantastic company at that time. But this was just too noisy up and down. And, to this day, I'm not sure if them getting out of semiconductors was fortunate, but we were going to be laid off. And out of that came this idea of what if we went to GE and with their support decided to spin it out because everything was going to be lost. And we're able to do that. And so I'm proud of the fact that, we never took any technology, or we actually deeply debated if it was ethical to even think about this. And the answer is, well, we did something good for GE, and in the process, it started Synopsys.
Yeah. So at that time, GE kind of realized that with semiconductor industry is a little too much to handle. It's not really the mainstream business they'd like to be in, right? So
Yes.
What is changing now after 40 years? What are you observing, Aart?
Well, earlier you mentioned Apple and Tesla that they have gotten into chip design. They've been into chip design for a long time already. So we're talking well over a decade, and in different ways, they have both become awesome at this. But if there's one thing that over actually the longer period of time of our industry, which really starts with the invention of a transistor in 1947, so that's with one transistor, there's not that much you can do compared to today, obviously. But what has happened is that every 5 to 10 years, there's sort of a new exponential that enters the main thrust of our industry, and suddenly there's, now we can do this. And the example I like to use from yesterday was, you take the transistor 13 years later, actually a guy by name Kilby and Noyce invented the integrated circuit. And one has to think how big a deal that was. We had transistors, and suddenly you can connect them into the same silicon. And a step like that then opens the horizon immensely for the future. And there have been a set of those, and they sort of layer. And so gradually, our industry becomes more systemically complex. You have to know about more things at the same time. And therefore, the ecosystem around it has to really play well with the semiconductor companies and vice versa. And then there are periods where people decide, we want to all do it in-house. And then there are periods when they say, no, we can delegate it to others. We have other companies in the ecosystem that can do it. And the best example for that is actually in the 90s, the coming about of the fabless wave. And of course, today, TSMC is best known. And it's interesting that TSMC was literally started 2 months after Synopsys. And we have always had a parallel path because the synthesis enabled people to go to other sources because we could automatically map into those technologies.
Oh, that's interesting. Right. Because without it, they can't go outside. They have the, right.
Exactly. Yeah. And so, these things sometimes they just happen and you don't notice. And before you notice, it's all there, right? And that is what is so fantastic about our industry, because we have this unbelievably fast, what I like to call techonomic wheel, which is technology and economics are joined at the hip. you cannot do technology if you don't understand the economics, because you're going to go bankrupt in no time, because you have to invest and you have to polish and tune the products until you can make money with them. And then hopefully you can scale quickly, because then you need already the money to put it back into the system and start inventing again.
Yeah.
So it's this constant invent, improve, back and forth.
If we go back in time just a little bit more, and you went from CAD to EDA.
Yeah.
How did you make that transition? What is the story behind it?
Okay. Well, so what do these words stand for? CAD stands for computer-aided design, and it expresses exactly that. In the early days of computers, they started to help the design of chips because it was all done on paper and by hand. And the minute you could put data on the computer, and specifically initially the layout, for example, once you have it on a computer, it's a lot easier to modify and change things and so on. And so that was a form of productivity that essentially helped you do what you already did. And the other grouping of that, I would put simulation, which is, can you describe your circuit in a model on the computer, and can the computer at least predict something of what's going to happen? And if the what's going to happen is correct, then you're good. If there's an error, you'll find out by doing a simulation. And so these were sort of cornerstones of a phase that, of course, became much more sophisticated than what I just said. The difference between computer-aided design and EDA, electronic design automation, is the word automation, which is now, it's not so much helping you with a task, it is doing the task for you. And one of the linchpins was what we happen to be on at the right time with the right way, is synthesis, which is, can you describe the circuit you want to do with some equations, and can we automatically create all the connections between different logical gates? And so that brought an unbelievable increase in productivity, because typically at that time, which was, we were about 4 to 5 micron transistors, to give you a sense. That would look at very big today, but at that time, that was state of the art. And so you were talking about a few hundred gates that people would optimize, and they would literally take weeks to optimize and make it a little faster, and fewer gates, and can you change the logic this way and that way. And the computer program we wrote was ultimately one that could make that faster, better, very, very quickly. And so when it was introduced, literally in a few hours, we could do what they took many weeks. But the other thing was, it was 30% smaller, fewer gates, and it was also circuits that were 30% faster. Power at that time was not really in the story. And then the third thing it had was, you could automatically map to a silicon technology of choice, which is the point we made earlier on the going to the fabless providers. Yeah. And so it was a watershed. At the very moment, I think that digital design itself had this opportunity of growing like a weed, which it did, an exponential weed in this case. Of course, this was the age of computation. You couldn't get enough of it, right? Ever. And still, we're in the age of computation, certainly as AI is concerned.
But what you just described is really the basic building blocks of the EDA industry today. And that happened in the span of how many years, Aart?
Well, it's always difficult to say that, because what we are as an industry is, we always want revolutionary change in an evolutionary fashion, right?
Yeah.
Whatever, our customers say, oh, I want this most advanced thing, just don't change anything. and of course, that's an impossible assignment. But this is true for many things that we do in life today. Is on one hand, we want the most advanced app, and then suddenly you don't remember, well, where can you find the delete or some stupid thing that you've been using for the last 20 years. Yeah. And so change is challenging. But I would say that the synthesis wave, we came really to the market in 1987, and within 2-3 years, all of the most advanced design groups were using it deeply. Wow. So fast. Yeah, that was very fast. Wow. And then comes the next thing is, well, this is great, but and you learn the lesson that often the most dissatisfied customers are your best customers, because they drive their state of the art. And the lesson I've learned there was, glue yourself to the people that move fastest. It's like, if you ride in the Tour de France, never let three guys get away,
Yeah.
Stick to them because you'll never catch up once they are working together.
Who are those three players that you need to stick to?
Oh, well, they change all the time. And I'm always careful with naming them because there's always a fourth player that's right behind that one should not underestimate.
Are we looking at another wave now of some tremendous changes likely to happen with AI now?
Yes, I think so. But before I go on the AI side, so let me give you a picture. I've always looked at what we do, certainly since computation came about. So after the integrated circuit and the first computer was really a calculator, right? And then did a lot more. And very quickly, what we saw really is that there's silicon and then there is software. And initially they were well separated by some compilation. Now they're intimately intertwined. And the reason that's important, because to me, it's sort of two sides of the same techonomic coin. You need to have both sides working not only together, but working economically well and technically well. And so just as much as the move from transistor to integrated circuit was sort of the opening of multiple decades of moving forward, we are now looking for, so how can we do much more still than what we have today? And this is where, in my opinion, multi-die is, or some people call it chiplets, but actually I like multi-die better because you have very big chips coming together. Chiplet sounds so small. It's actually very big. And in super high proximity, and even more than that, now on top of each other. And there are many challenges with that we can go into, but it has certainly the tremendous potential that you can have another massive wave of more transistors available, but also the opportunity and the necessity to rethink architecture. Because if you can now put chips together and you can have literally hundreds of thousands of connections per square millimeter, which, it's useful to imagine what that is. And it is really small, but it's quite fantastic. With that, architecture will be rethought. And and so now attaching it to your AI question, of course, AI is rethinking architecture from the software side anyway. And many products are now referred to as software driven because the software essentially says, that's the function I want. And the silicon says, and this is the physics I can provide you, right? And so software to silicon or silicon to software, they are two sides of the same coin.
All right. So, well, software or hardware, that's really a big one, right? And I think we need to move on to the multi-die that you mentioned, because that's also, I think that bringing in new factors the designers need to think about. It's not just about laying out the whatever they need to be connected, but we're talking about thermal, we're talking about more physical, how durable this is. I mean, tell me more about the challenges of multi-die era that we are in.
Yeah, I sort of feel the entire history of our field. Here we have something fantastic, and then you lay a nightmare, right? Or no, opportunity to actually fix these things. And, one of the things I learned early on in my career is, just because something is clearly impossible doesn't mean you shouldn't have the courage to try. And that is what our industry has done over and over again. And so you mentioned thermal, you can mention stress. There are many of these issues, and I've always been encouraged by the fact that we see an objective that is so promising, and that therefore we have work to do, because that is what our industry has done. And when I mentioned earlier this total exponential behavior of our industry, it is so many little exponentials that all multiply in. And so now we have to deal with the thermal issues. We will have to deal with, at a macro, the overall energy that all of this will take. The cooling will be a part of the answer to the thermal. And so this is how systemic complexity continues to grow. And you're absolutely right. There's a lot of learning, a lot of invention, but also a lot of collaboration and trust between companies to make it work together.
How is the EDA market going to, or the EDA industry going to help in solving some of these challenges that you talked about in rethinking the architecture?
Well, so like we have done in the past, which is make sure that we are glued to the designers and especially the people now that are thinking about these architectures and understand which aspects have the biggest technomic potential and try to focus on those first, but also keep in mind what are all the other things that one could do to keep raising the bar of what we deliver to them. And, the good news of our customers, they really go through these cycles of being elated by what we deliver to then 10 minutes later be, well, yeah, but you could do better here. And what if this and what if that? And so there's a continual hunger for driving forward the state of the art because the potential of applications is so big at the present time. And I think you mentioned earlier the word AI. And of course, AI is a whole new form or wave of application of computation. And I think that in many ways, it captures the destiny of what the information age is all about. And the information age, for argument's sake, we'll start it with the transistor. So we're like 77 years into it. And now we start to see the destination is becoming clearer and clearer, which is to augment and scale the human brain. Now, that's an enormous statement when you think about it. And in all fairness, the little pocket calculator was a pretty damn good start, right?
Well, I actually would like to go back to where you are at in terms of collaboration, right? And I think collaboration is easier said than done. And if it is collaboration within your company, sure. I mean, that's a given. But now,
which one is easier, inside or outside?
All right, that's a separate discussion.
Okay.
But what I'm worried about is collaborating with others in a bigger ecosystem. We started out this conversation with the semiconductor industry. It's not just chip companies, but with all those other companies, right?
Of course.
So when you talk about collaboration, we're talking about not just designer. Designer have to, I'm guessing here, but probably have to think through all the way to the packaging and manufacturing. In other words, when you start designing it, it used to be 30 years ago, it wasn't their problem, however they package it. But now it is their problem from the very beginning, right? So tell us about that. And then, Synopsys doesn't do packaging. Synopsys doesn't do manufacturing. There are a lot of things Synopsys doesn't do. So how do you collaborate with those different players in the industry?
Yeah, but when you say doesn't do that, that's the same as saying, well, Synopsys doesn't design circuits. Actually, we do design circuits, but Synopsys has to know everything about it if we want to automate it. And so we have to know a lot about manufacturing in order to be able to do layouts that actually do work that pass the test of time and meet mmany of the constraints in order for manufacturing to yield well. And so another way of responding to you is, there's a big piece of Synopsys that looks down deep into the silicon. And, we literally have what's called TCAD, Technology Computer Aided Design, which are tools that simulate individual devices or groups of devices down to the molecular level, right? Atomic layers. And so we know about that. And then you start building up from there. And of course, you have the individual transistors and the libraries, and then you have the gates, and then you have a large collection of IP blocks. Synopsys is the second largest provider of IP blocks next to ARM, although we have many more different ones. They have a very focused business. And then you move up, and now you start interacting with the architects, and they need the simulation of how their architecture will work even long before they know how they even implement it. And they still already then would like to know, and how much power is this going to consume? And how fast will it be? And then you move even higher and you arrive, let's say, at end markets such as automotive. And then those people say, yeah, but whatever we do, this circuit has to work when the car has been standing in Phoenix in the sun for a week, and I still want to make sure it starts, right? And so all of that is sort of the physics to the application. I always like to sort of draw as sort of this upward and the downward, and we work at all of these levels. And that is just another way of saying that all these systemic complexities that have layered over time, if you forget one lesson from, 1997, the circuits won't work. And that's that crazy revolutionary change with evolutionary keep everything you have learned. And so you mentioned a couple of the newer ones. Packaging. Packaging is not new, but what recently is referred to as packaging is really multi-die.
Right.
And I prefer to call it, new connectivity, because the essence is actually how you can connect things, and the high proximity and so on. The packaging gives a little bit the sense, oh yeah, you just put it in a box and then it's going to work. No, it's not like that. It's a lot more sophisticated. But that sophistication is a new way to shine.
Yeah.
And you have heard certainly in the industry that some people have been fantastically successful with these very complex multi-die, and then every so often there's a unexpected failure, and then for 3 months people dig in and they find it was some corner condition that actually was difficult to find, but now we can. And the learning continues.
Right. So that kind of connects to what I actually really wanted to do was the Synopsys acquisition of Ansys, because that sort of paints the picture of how the tool company really has grown to the point that you have to take care of the entire modeling, entire system level, the simulation. Tell us a little bit about the thinking that went into your mind when you started well, do we need this piece of technology, or do we need to work with this company? Tell us more about that. Yeah.
Well, already quite a number of years ago, we built a very good relationship with Ansys. And actually, a lot of credit for that goes to our new CEO, Sassine Ghazi. You probably know him, because he saw that the necessity to add more and more physical, multi-physics capability around that, always with the same goal. The digital twin is sort of this ideal of, can we model everything? But the reality is you model in different layers, you model in different verticals. And but you yourself just said earlier, hey, now you have to deal with things like thermal and a number of other things. Well, those fall in the category of multi-physics. And so we had teamed up with Ansys for quite a number of years because they had some really great capabilities there. And so as this all becomes tighter, there was an opportunity to join forces, and that's sort of the thinking behind it.
I know we may be running a little bit out of time, so I kind of like to ask you to look into the future for us. You've experienced so much in this industry. You've had to move it along to this point where, when I look back, it just seems like more and more things are happening at a very accelerated pace. So when you look ahead, what do you see?
Let me just pick up on your word accelerated, because we are an exponential. And the funky thing about an exponential, it has always the same acceleration. It's just that it multiplies, so it feels like it's faster. And of course, in absolute terms, it's changing super fast. And I would agree with you that actually even that has come in waves, right? And that the present wave is that I would say since Google sort of cracked the Go game, that certainly sent everything to the races, because from that pattern matching became so powerful, and then the various forms of learning came into being, and then suddenly it hit via Gen AI a whole new space. And that space is so enormous, can apply to every vertical market, that there's literally an onomic pull. There's economic opportunity if you could change, the trucking, if you could change agriculture, drug research, and so on. I'm not saying that any of that is super easy immediately, but the doors are opening. And so for many decades, the silicon technology sort of enabled this. And so we will build it and then they will do something with it. And now they are doing something and they want us to build more, right? And so the techonomic loop is spinning really fast as we speak. And so that is why the future is so interesting, because I had the opportunity to speak last night, and one of the things that I tried to do is to illustrate how, about 220 years ago, the industrial age essentially accomplished its grand mission, which is augment the human muscle, augment and scale it massively, obviously. And I would say that our industry, after now 77 years of sort of information age, if you take those dates, has also found its mission, which is augment and scale the human brain. Now, it almost sounds like an arrogant statement, or no, just a crazy far statement. And of course, it will be in different forms and different layers and so on. But it is a destiny that is of enormous impact. And you can see the races going forward. You can also see, and that's a fun fact or a horrible fact, which is that our industry suddenly also wants way, 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 way more energy. Yeah. And of course, there we have a massive human challenge with what's happening on that side of our existence. But the parallelism is actually quite interesting in that sense. So I think we see where the next decades are going to go. And I would, because of that, predict for sure that the semiconductor industry, which is central in these two cones, will do very well. And many people have asked, well, will we really pass $1 trillion by 2030? Absolutely, we're well on path for that. Is a lot to do? Absolutely.
All right, very good.
I get the message over time, so maybe
that one. The idea of augmenting human beings. So that's a very hopeful, optimistic view. But thank you very much for coming to the show, Aart. And
thank you, Junko. Thank you, Bolaji.
Thank you. It's really been a pleasure.
Same here. Thank you, and be well.
Okay.
Bye.
You too.